Hey folks, I hope you're all doing well. This is a short video about circles, which is section 5.1 in the book. So a few preliminaries first. The Pythagorean theorem, I'm sure you have all heard of. It's one of the most famous theorems in mathematics, and it relates the legs of a right triangle, right? So a right triangle, of course, is a triangle that has a 90-degree angle, and the hypotenuse of the triangle is the side opposite of the 90-degree angle. It's the longest side of the right triangle. And the theorem just says that if you take the sum of the squares of the legs, you get the square of the hypotenuse. A squared plus b squared equals c squared. So here is a picture that sort of proves or at least demonstrates the truth of the Pythagorean theorem. In the left-hand picture, you can see I have four white right triangles, each of which are the same size. They have one leg A. I'm looking at the upper left one of the upper left ones now, and they have another leg B, and then the side C is opposite the right angle, so it is the hypotenuse. And 1, 2, 3, 4 of these triangles are all the same. So this square in the lower left has side length A, right? Every side is length A, so its area is A squared. And the square in the upper right has side length B, so its area is B squared. And if you take some scissors and cut the shapes out and rearrange the picture a little bit, in particular, put the white triangles around the edges instead of in the upper left and lower right, then you get a picture like the one on the right, where here I have leg A, and leg B, which means this must be the hypotenuse C. Over here, again, A, B, so the hypotenuse is C. So this gray square must have area C squared. Well, the white area in both figures, left and right, is the same because it's the same four triangles. So the gray area must be the same as well. And that means A squared plus B squared is equal to C squared. This theorem is generally attributed to Pythagoras, who was a Greek mathematician who lived about 2,600 years ago. It was almost certainly known long before him. We know that the Babylonians knew about the theorem many years before the Greeks came on the picture, and the Indians knew of the theorem about the same time as Pythagoras, and it's probable that it was discovered in many different cultures at various times in antiquity. So in any event, here is an example of an application of the Pythagorean theorem. It basically means if you have a right triangle, so the angle in the lower right here is meant to be a right angle, I should have marked that. Then if you know two sides, you can figure out the third side because we have an equation that relates the side lengths, right? In this case, that equation looks like this, right? The legs are 14 and x, and the hypotenuse is 31. The hypotenuse is always sort of squared by itself on one side. And so I can solve for the missing side, x squared. I subtract 14 squared from both sides to get the x squared by itself. And then I do a little math on the right. 31 squared minus 14 squared is 765. And then I just take the square root of both sides. And of course, I just want the positive square root because x is a side length, so it doesn't make sense for it to be negative. And I find that x has to be 27.66. Okay, for our purposes, an important application of the Pythagorean theorem is the distance formula. And the distance formula is a way to get the distance between any 2 points in the plane. And here is the formula. So it's the square root of x2 minus x1 squared plus y2 minus y1 squared. It doesn't matter which point is x1, y1, and which point is x2, y2. This formula will give the same value either way. And that's because x1 minus x2 squared is the same as x2 minus x1 squared. In this particular form, it doesn't matter what order you write those things in. And the reason for this distance formula comes from this picture. So here I have 2 points, the two blue points. The blue point, you can see it has x coordinate x1, it has y coordinate y1. The upper right point has x coordinate x2 and y coordinate y2, right? So this is x1, y1. This is this is x2, y2. So this distance, the horizontal distance, is just the difference between x2 minus x1, right? Horizontal distance is big X value minus little x value, and the vertical distance is y2 minus y1. Vertical distance is big Y value minus little y value. And so the Pythagorean theorem says that if I square x2 minus x1 and add it to the square of y2 minus y1, I get the square of d. And if you take square roots on both sides, you get this formula. Okay, so that's where the distance formula comes from. So we can use this to find distances. And we could in a more complicated way, use it to find perimeters of figures, right? We just find the distances from point to point around the figure. So how do I find the distance between these 2 points? I just kind of plop them into the formula, right? Here's the difference between the two x values, -3, -6. So that's x2 minus x1. Here's the difference between the two y values, y2 minus y1. Again, it doesn't matter which point is x1, y1, which one is x2, y2. And then I just do the calculation, right? So I think I did this more or less by hand, right? So I get -9 squared, and then 10 minus -1 is 11. Be careful to work in the parentheses first. Of course, -9 squared is positive 81, right? When you square negative, you get a positive. So I wind up with this under the square root. Do a little more calculating, I come out with 14.2 or so is the distance between those 2 points. Okay, we need distance to make sense of a circle, right? A circle, you all know what a circle is, but precisely, it's a geometric figure that has sort of two key parameters that define it. One is the center of the circle, right? So the center, of course, is the point in the middle, and generically we'll label those that point h comma k, right? So we'll put it in the plane somewhere. We'll call the x coordinate h and the y coordinate k. And the other key feature of a circle is its radius, and the radius is just some positive number. Certainly, a circle can't have a negative radius, so r does have to be positive. And then the circle is defined. So if you say, what is a circle? It's the set of all points whose distance from the center is r, right? That's what it means to be on a circle, is you're the same distance from the center as all the other points on the circle. And so because of this definition, we can write down an equation for the circle. We know how to find distance, so we just have to take the distance from hy to the center hk, xy rather, to the center hk, and set that distance equal to r. So we'll use our distance formula. Right, there's just a copy of the distance formula from up above, but I'm going to plug in the points xy and hk, and that's what it looks like when I do that, right? So the two x values are x and h, and the two y values are y and k. And then just to simplify things a little bit, I'm going to square both sides of that equation. So when I square the right side, the square root is going to go away, and I get this. And this will be our sort of standard form for the equation of a circle. And so when we write this down, you can see right in the equation the coordinates of the center, h and k, and the radius, right, the square of the right-hand side. So for example, here are a couple of equations of circles, and we can just eyeball these and figure out the center and the radius. So I'll open the cells in a minute, but just looking at this, I can see that there's my h value. There's my k value. So the center of this circle is going to be the point 1, 5. So indeed, the graph of this is a circle. So that's the first thing actually that's worth pointing out, is that when we see an equation in this form, we know that the graph is a circle. Notice that a circle is not a functional relationship between y and x, right? Circles fail a vertical line test because you can easily draw a vertical line that hits the circle in more than one point. Okay, so the radius is going to be 7, because on the right-hand side, that's r squared, right? So if that's the square, the radius is 49, and the radius must be 7. And as we said a moment ago, the center is the point 1, 5. Okay, so here's another example. A slight complication here is in the second term, we have a plus between the y and the 2 instead of a minus, but that's not a big deal. We can easily rewrite it like this. Instead of y plus 2, I'll write y minus -2, and now it's in the standard form for the equation of the circle, right? So I can recognize that this is a circle, right? I can see the radius because that's going to be just the square root of the right-hand side, so 10 in this case, right? Radius is 10 because that value is r squared. And then the center, well, here's my h value. It's what's being subtracted from x. And here's my k value, -2. So the center here is going to be 8, -2. Certainly the center can have negative coordinates. The radius has to be a positive number. All right, one more example of this kind. And again, the sort of complexity here is, again, we have a plus sign here between the y and the 7, but now we know that's not a big deal. Doesn't look like we have an x minus h, we just have an x squared. But that's easy enough to rewrite. right, I can rewrite x as x minus 0. And now, and then as before, I rewrite y plus 7 as y minus negative 7. So now it has the right form. I can see the radius is 5, the square root of that number, and the center is 0, comma negative 7. So let's just write that down. Indeed, there we go. We can, and so we could also graph these equations easily enough because we know what they look like, right? We just sort of mark the center at 8, negative 2, and do our best to draw a circle around it with radius 10. We can go the other way, right? If we see a circle in the plane, we can estimate its equation. All we need to do is figure out the center and the radius. I'm going to guess the center of this one is about right there. So that looks like the point 4, comma 1. And if that's the center, then the radius, the easiest way to find the radius is just to go straight up or down or straight left or right. So if I go up, I get to the y value 8. So from the y value 1 to the y value 8 is a radius of 7. So it looks to me like this circle has a center at about 4, 1. Again, we're eyeballing it, so we might be off by a little bit. And it looks to me like this circle has a radius of about 7. And if I know the center and the radius, we can use our standard form for the equation of a circle to write down the equation, right? There's x minus h squared, here's y minus k squared, and 7 squared is 49. Okay, and so we can go from equations to figuring out things about the circle and drawing the picture if we need to. We can go from the picture to the equation. We can also go from a description of the circle to either one, right? If we're given the radius and the center, this problem that I've highlighted now is actually a little easier than the one we just did where we had to kind of estimate the center and radius. All I have to do here is load this into our standard form, which I've copied there. So r squared will be 36, right? Because r is 6, h is 3, k is 4, and away we go. Now, you should be able to FOIL out this right-hand side if you need to write that as a sum of a bunch of terms. You don't have to do that unless something specifically asks you to, or if it's to your advantage in some way. So if the problem is just, write down the equation of this circle, leaving it like this is fine if the problem doesn't give any other instructions. Okay, so quickly graphing this equation here, I can see moving a little faster. The circle has center 0, negative 5, and radius 7, right? So I sort of identify those three things from the equation. 1, that it's a circle. 2, what the center is, and 3, what the radius is. And once I have that, I just go to the plane, I mark my center 0, negative 5, and I do my best to draw a circle around it with radius 7. And of course, with a computer, I can draw a very nice circle, right? So here's my center 0, negative 5, and the radius of the circle is 7. Okay, how do you find intercepts of a circle, right? Any graph can have intercepts, not just functional graphs. They're points where the circle crosses the axis, right? So how would we find, let's say, the x and y intercepts of this circle? Well, again, x-intercepts always occur on the x-axis. I can see one over here where the cursor is, and there's another one over here. And y-intercepts occur on the y-axis. So there's one y-intercept up there where the cursor is, and there's another one down here at the bottom. Well, again, x-intercepts occur where the y value is 0, y-intercepts occur where the x value is 0. So I just have to make those substitutions in order to figure these things out. So x-intercepts occur when y is 0. So what I will do is take my equation and substitute y equals 0, right? So you can see the original equation, it's a little obscured there at the top of the screen. If you put in a y equals 0, it becomes this. And now I have an equation with just one variable in it, which means potentially I can solve it. And this one, indeed, we can't. So I did a couple things here. First, in this second step, that's 6 squared, right? So that's where the 36 comes from. The 100 is the same as it was up above. When you square a binomial like this, recall from algebra that you do the square of the first, twice the product of the two terms, and then the square of the second. So the square of the first is just x squared. That's that one. The product of the two terms is negative 3x. So twice that is negative 6x. That's where that comes from. And then the second squared is 3 squared. 3 squared is 9. Okay, this is a quadratic equation. And recall, we talked about quadratic equations earlier in the course. So I'm going to tidy this up a little, right? 9 plus 36 is 45. That's all that happened there. And then I will move the 100 over to the left-hand side. So I subtract 100 from both sides, because to solve a quadratic equation, what you want to do is get all the terms on one side and just 0 on the other side, because when you do that, you can use the quadratic formula. If you don't remember it, you can go look it up. This quadratic happens to factor, right? So recall another little piece from algebra. But if you didn't see the factorization, no big deal. The quadratic formula would give you the right solutions. So I can see, since this is in factored form, the solutions are x equals 11 and x equals -5. And those are my x-intercepts. Technically, a little more precisely, the x-intercepts are the points 11, 0, and -5, 0. And this looks about right? There's 11, 0. There's -5, 0. Okay, for the y-intercepts, I'm going to set x to 0. So in my original equation, when I set x to 0, that looks like this, right? So here the x value has been set to 0. This again is a quadratic equation. So I'm going to use the same strategy as up above, right? So moving a little more quickly here, when I square this, I get 9, and then I expand the binomial and I get those 3 terms. I'm going to sweep everything onto one side of the equation, and I get this. Right, so I just have 0 on the right, and then I can use the quadratic formula. Again, if it factors and you see how it factors, that's great. You can go ahead and factor it and solve it that way. The nice thing about the quadratic formula is it always works, whether the thing factors or not. So A is the leading coefficient, that's 1, B is 12, C is -55. I load that all into the quadratic formula, which you can go and look up if you don't remember it. There it is. And when I do that, right, so here I plugged in the A, B, and C. You can check that math later yourself. And when I do all the calculation, I come out with 2 numbers, right? Because of the plus or minus, it's common to get 2 solutions here. And the solutions turn out to be, if I take the plus sign, I get 3.54. If I take the minus sign, I get -15.54. And those look about right too, right? So here's the 1 y-intercept, that's the 3.541, and here's the -15.541 down here. Okay, so intercepts, there's a little more algebra to do in finding the intercepts of a circle, but the basic strategy is always the same. Let's see, let's pass over that. No, we can go ahead and do this example. Let's go ahead and do this example now. So at what point in the first quadrant does the line with equation y equal x plus 2 intersect the circle with radius 6 and center -1, 0? So this is kind of a geometry problem that we're going to do algebraically, right? We have a circle and we have a line that sort of crosses through the circle at a couple of points, and we want to find where those points are. Notice that this we recognize as a linear function, right? The slope is 1, the y-intercept is 2, and then circles we've been talking about today. So you could draw the picture of this if you wanted to, and I think we'll show the picture down below, but it's not absolutely necessary. The first thing I'm going to do is figure out the equation of this circle, right? So the center is -1, 0. So there's my x minus h, right? X minus -1 is x plus 1, and y minus 0 is just y. And then the radius squared is 6 squared, which is 36. Okay, so now I want to find where the graph of this equation and the graph of this equation intersect. There's more than one way to do that, but the way that we will generally use is called substitution. I take one of the equations and solve it for one of the variables. Now we've already done that, or we didn't really do it. It was given to us, right? Y equals x plus 2. And then I substitute this expression for that variable in the other equation. So I'm going to replace y with x plus 2, because at the intersection point, both equations have to work. So at the intersection point, y is equal to x plus 2. So that's where this comes from, right? See how the y has been replaced by x plus 2. And in this way, I get an equation that just has one variable. This is a quadratic equation, even though it's not in a great form right now. So the first thing we're going to have to do is some algebra. When I FOIL out that first binomial, I get that, right? I'll leave you to check the algebraic details. And when I FOIL out the second binomial, I get that, right? Square the first, twice the product of the 2, square the second. Now I'm going to combine like terms on the left-hand side, right? I have multiple square terms and multiple x terms and multiple constant terms. So I'll put them all together. Excuse me. And I wind up with this. This is more clearly a quadratic equation. So we use our usual technique of sweeping everything onto one side. So I'll subtract 36 from both sides. And now I think I'll use the quadratic formula. I don't see an obvious factorization of that. Right, so my A value is 2, that's the leading coefficient, and then B is 6, C is negative 31. Load it all into the formula, and it looks like this. Again, because of the plus minus, you're going to have two solutions here, right? One is going to be negative 6 plus the square root of 284 divided by 4, and one is going to be negative 6 minus the square root of 284 divided by 4. And those two solutions come out to be those two numbers. So again, good practice when you're watching this is maybe pause the video at these points and check these calculations. Make sure you can do them yourself and you're coming out with the same numbers. Okay, what I have found is I found the x coordinates of the points of intersection, right? So a line in a circle, generally speaking, will intersect more than once, right? The line will sort of enter the circle and then go out the other side. So I found the x coordinates of the points of intersection. To find the y coordinate, I can use either equation, this one or this one. So I think I'm going to use this one because it's much easier. And I just plug the x values in there for x. Right. Also, so it's worth noting here, I should read the question carefully. This is asking for a point in the first quadrant, right? So the first quadrant is the upper right quadrant where both coordinates are positive. And that means I don't want that one. Right, the negative x value isn't in the first quadrant. So I take my desired x value, I plug it into that equation, y equals x plus 2, and I get the y value. And I have solved the problem, right? The point of intersection has coordinates 2.71 and 4.71. And here is a quick picture. Right, so the circle doesn't look circular because the scale on the axes is not the same, right? So this is 2 units on the x-axis, but 2 units on the y-axis is not as far, which is why the circle looks squashed a little bit. But this is the line y equals x plus 2, the blue line, that looks about right, has a slope of 1, y-intercept where the cursor is at 2, and you can see it hits the circle over here on the left, and then at this purple point on the right. The purple one's what we're looking for, right? That's the one in the first quadrant, and the coordinates look about right? 2.7 or so, that's in the right ballpark, and 4.7 also in the right ballpark. And you can see this other one, we know its x coordinate is negative 5.71, and again, that looks like it's in the right ballpark as well. And then we didn't find the y coordinate, but that would be easy to do using y equals x plus 2. All right, one more example of circles, and I think that will be good for today. This one is a little bit harder in that we are going to have to kind of come up with a visualization and then come up with the equations and then kind of solve the problem, right? So when you see a word problem like this, there's no kind of one formula that will do all word problems. But a good first step, and this is not always applicable, you can't do it in every single case, but if you can, it's usually a good idea, and that is draw a picture. And this seems like a pretty visual problem, right? I've got one street that runs east-west. All right, well, that's going to be left-right when I write it down, and another one that runs north-south, so that's going to be vertical when I write it down. And then I've got a pizza store that's located on the east-west street, and it's 4 miles west of the intersection. So the first thing I would do is draw 2 roads, one running left-right, one running up and down, mark the point where they meet, that's the intersection point, right? Go 4 miles to the left, because that's west when we look at a map, and plunk down your pizza store. And when you start doing that, you get a picture that looks something like this, right? So Main Street runs left to right. That's the purple line, purple with the arrows on it. Meridian Road runs north-south. So that's the kind of olive-colored line going up and down over here. Here's their intersection, right where the cursor is now. So if I go 4 units to the left, there's the pizza store, right, the blue dot. So I'm going to put the store at the origin of my coordinates, right? So this is an advantage you have when you're drawing a picture of a problem in the plane, is you can put the coordinate system anywhere you want. So you could put the origin wherever it's easiest. It's easiest here to put make the pizza shop the center. And the reason for this is that the store advertises that it delivers within a 5-mile radius. So that means if I draw a circle around the pizza shop of radius 5, that represents its delivery area. So if you're inside the black circle, they'll bring you a pizza. If you're out here where the cursor is, you're out of luck. And this stretch of Meridian Road, rather, what's shown here, oh yeah, so there's a little typo here. So as far as the question as it's phrased, how much of Main Street do they deliver to? Well, they deliver to a 10-mile stretch of Main Street, right? We go from -5 to +5. There's not much to do to figure that out. If we make Main Street here Meridian Road, now the problem's a little more complicated, right? I can see this stretch of Meridian Road that they deliver to, but I'm not sure exactly how long that stretch is. Okay, so the equation of the circle is pretty easy to write down here, right? The center is 0, 0. So on the left, I'm going to get x minus 0 squared plus y minus 0 squared. The radius is 5, the delivery radius. So the right-hand side is 5 squared, which is 25. And looking at my picture, what I would like to know is what these y coordinates here where the cursor is and down here where the cursor is are. And those y coordinates, of course, occur when x is 4. So what I'll do is I'll just set x equal to 4 in this equation, right? So I set x equals 4, and right there, you can see where the 4 has replaced x. And this equation is not hard to solve. It's a quadratic equation, but it's easier than the ones we saw up above. 4 squared is 16. And when I subtract 16 from both sides, I get y squared is 9. And so that means y is plus or minus 3. And that tells me that this point has y coordinate -3, and this point has y coordinate +3, right? I just found those two y coordinates, and that means they're 6 units apart, of course. And so the answer to the question is the stretch of Meridian Road in the delivery radius is 6 miles long. Okay, that is a good introduction to circles. I will open up this last example in the notes for you to look at. Take good care of yourselves, folks.